Good morning. This is Major John Cranston, and I was going to go ahead and take a look at the assignment Pendulums and Springs with you and see if I can give you some advice as to how to go about these different problems, and then I'll make that assignment for you. So let's go ahead. In number 7, they refer to some information that's given to you in problem number 6. So in problem number 6, it turns out that they said that M, the mass, is going to be 15 kilograms. And then they also, in number 6, they said that K, when you solved for number 6, you found K, and K was going to be 370 newtons divided by meters. So if you want to know, if you want to know the period of this particular spring, then the period of the spring goes like this. Let's see, period equals 2 pi square root of M over K. And so I think you can see from that if that's how you solve for the period of a spring, and then if you put in the M that I just mentioned to you and the K that I just mentioned to you, that should be pretty easy to find the period. Then once you've found the period, just keep in mind that the period is 1 over the frequency. And so, or conversely, the frequency is equal to 1 over the period. You can go ahead and find out the frequency pretty easily. And so that's what you would end up doing on number 7. In number 8, they give you some information. They say a spring with a spring constant of 650 newtons divided by meters has a rest length of 1.7 meters. So first of all, K is going to be 650 newtons divided by meters, and then the rest length, we can put here rest length is equal to 1.7 meters. And then it tells you that the spring oscillates with a frequency of 1.4 hertz. So again, if the frequency is 1.4 hertz, then it's going to be pretty easy for you to go ahead and find the period, because the period is going to be 1 over 1.4 hertz. And I think that, see if I can stick this here, if you can read this at all. And so we'll just say 1 divided by 1.4 equals, and then that would give us 0.714. So T is 0.714 seconds. So they want you to find the mass of the object, and I think this is the first one that's asked for the mass of the object. So let's just take a look here. If you've got T is equal to 2 pi square root of M over K, then what we're actually looking for is M. Then we can go ahead and vary it in such a way that we get M. So here I'm going to divide by 2 pi, and here I'll divide by 2 pi. Then this now will go away, and then I have T over 2 pi is equal to the square root of M over K. Now I need to square these things, so I'll take T over 2 pi squared, and then I'm going to square M over K. So let's go ahead and I'll just move that down a little bit. T over 2 pi squared is equal to M over K. And so we're almost there. We just have one last transformation to do, so we'll go ahead and make a K here, write K here and write a K over here, and then we can go ahead and cross these K's out, and then that's going to be the formula that you would use to find this. And if you take a look back here, this should be pretty easy, because here you've got K. K is 650 newtons divided by meters, and T, the period we figured out earlier was 0.741 seconds. So you're not going to have too much trouble finding what were we looking for? You're not going to have too much trouble finding the mass in that particular case. Okay? So I think you're okay there. Let's go ahead to number 9. Number 9, if the mass in number 8 is now at rest while suspended from the spring, what is the length of the spring? And so in number 8, we said that the rest length of the spring was 1.7 meters. And then we said that, let's see, if the mass is now at rest while suspended from, what is the length of the spring? So we need to be able to find what x is. So x is how much the spring stretches. And we have a formula for that. We have F equals kx. And so now you found the mass earlier. You found the mass in number 8. Now if you want to get F, what you're going to have to do is you're going to have to take that mass times g, and then that will give you a force. Then that force can be moved over, and that will be the F that you have, and F is equal to kx. You also have k, because that was shown to you in number 8. It said that the spring constant was 650 newtons per meter. So if you have the F and you have the k, then you ought to be able to solve for the x. And so you're going to rearrange this a little bit. You say something like F over k is equal to x, and then you should be able to go ahead and find here, you should be able to find what x is. Once you have found what x is, then you'll just go ahead and take the rest length. The rest length plus x equals the length. Maybe we could say the length when stretched. Anyway, I think that you should be able to find your way through that then. And remember, what I'm writing here isn't the kind of thing that I'm expecting you to write. I'm just writing some explanatory things. So I do want you to list out the variables and tell what formulas you're using and that kind of thing. But I think I'm giving you enough information that you ought to be able to make sense of it. Now we're going to go on to number 10. It says you wish to build a clock with a spring that has a spring constant of 23 newtons divided by meters. So we'll say here K equals 23 newtons divided by meters. How much mass will you need to make this clock have a frequency of 1.0 hertz? So now that's going to be the frequency, 1.0 hertz, and then if we want the period, we're going to say period equals 1 over the frequency is going to be 1 over 1.0 hertz. So the frequency is actually going to be 1 second. So if you have the frequency here, this simply becomes a mass problem, and we've figured out the formula for mass earlier, and we said that mass was going to be equal to the square root of the period over 2 pi squared and then times k. And so you have the period here, which we found out was 1 second. You have k, which is 23 newtons divided by meters, and now all you have to do is go ahead and figure out what the mass of that would be. And so that's what you would do for number 10. Now number 11 is another mass problem here. So it says, your boss at work needs a way to accurately measure 5.0 seconds. So starting off then, the period is 5.0 seconds. Clocks are out of the question, and all you have is a 1.0 kilogram bucket with 15 kilograms of sand and a 2.00 meter long piece of rope, a spring with a spring constant of 22 newtons divided by meters. How would you suggest this measuring equipment, and what are its specifications? So K then is 22 newtons divided by meters. So you actually need to solve for M, and M was going to be T over 2 pi squared and then times K. Now notice you've got T there, you've got K right here, and so you have the things that you need, and then you will actually go ahead and solve for M. So you're going to solve for M, and you're going to get a number for M, but that's not the end point here. So let's, what you end up having to do is you end up having to figure out if M is a certain amount, how do we find M? Or how do we get M? How do we get M number of kilograms of stuff here? So let me put some things here. 1 kilogram is going to be the bucket. And so whatever M is here, then you'll say M minus 1 tells you how much you need. And so the bucket is 1, and M minus 1, since we're taking the bucket away, is the mass of the sand. And so then you're going to put the sand and the bucket together in order to get this number M. And then you're going to describe this. So let me give you some ideas here. You have a string, and you have a spring, and you have a bucket, and you've got sand, and you want to make something with a 5-second period. So you'd say something like, or I don't know if I mentioned the rope. The rope's important too. So you're going to have to tie the rope onto the tree, and then hang the spring from the rope, and then hang the bucket from the spring, and then you're going to have to add the right amount of sand until you end up getting the right mass, which you found earlier. So when you find the mass, then you have to fit it into this account here, and you're going to tell us, you're going to give a description of what you would do to make that measuring equipment. And I'm trying not to do the whole thing for you, but I think you can figure it out from what I've said. Then we go to number 12. On number 12, I'm going to stop. I'm going to pause this.